So let me first start out to explain what I mean by higher order topology. The plan with my talk is to indicate the use of higher categories. Now? Okay. So the plan with my talk is to indicate the use of higher categories in picking up topological information. And I thought to do this in 3 stages. I start out with ordisms with singularities, the revisited version. That's the piece of mathematics I brought in contact with Dennis for the first time, a long time ago. Secondly, I'll look at topological quantum theories with the singularities and see how that relates to higher categories. And eventually, the goal will be then to use these pieces of information to construct some new topological functors and give a new explicit model of elliptic homology, which so far we haven't had any explicit model of. So, let me see. I'll start out with sort of a little bit of history regarding complex cobordism and related theories with singularities. So let MU stand for the spectrum representing complex cobordism, and stable homotopy is polynomial algebra. And if you localize at a prime, you have the Brown-Peters version like this. And it was a problem in the late 60s, the following problem was posed. When one could find spaces, dk, such that the Brown-Peters homology of the space was Vp divided out by the ID generated by P, V1 up to dk. And P is a prime. I mean the prime at Brown-Peters perspective. And it was clear that this had close connections with deep problems in stable homotopy theory, stable homotopy groups of spheres. And V0 is just simply the 1P rule space. V1 was constructed by... Okay, well, I think that I mean, MU is a spectrum, and you take stable homotopy groups for that spectrum. What's the spectrum? Oh dear.
What's homotopy?
Okay, what's the spectrum? It's a sequence of spaces. The Ney version is that it's a sequence of spaces xn, and that you have S1 smash xn, you have a canonical map in xn plus 1. I mean, that's how these are connected. And MU is a special case, and then you define homotopy groups of these. And this actually, the stable homotopy groups classified the complex Bordism ring. And this was done by Miller and Novikov in the 60s, this result here. And this localized version by Peterson is fairly easy to corroborate that. Yeah, oh, okay, since my time is short, I think I'll have to proceed with that. And these things here were known fairly quickly, but further results were hard to obtain. And then Ravenel had some very nice results there about the non-existence of these DKs, also implying things in stable homotopy theory. And I think the most interesting result in that regard was Hopkins, Mahol, and Miller, who showed that V of P minus 2 primes bigger than 3 do not exist. The interesting thing is that the techniques use now, later on, to study these, rely heavily on the Morava type K-series. I'll explain what that is. But in 1969, I was looking at this problem, and it was much too hard on the present technology. So I rephrased the problem in the following way, that if you look at pi star, can you find a spectrum of space such that pi star of MUI is equal to the mu star divided out by the ID I? And remember that the other formulation of the P version of the VK is to find the space VK such that mu smash VK has the same homology groups. And this one I was studying for a long time, but then finally I heard about this new idea more than 30 years ago about borders and theories on manifolds with singularities due to Dennis. And that actually solves this problem here. And give rise, then, in a way, give rise to the Morava K theories, which again led to the results from VKs. So there is sort of a circular action here. Let me see. What are borders and theories with singularities? Let me just try naively to explain this idea. Here we have an ordinary bordism, and these bordism theories say G is a unitary group, were calculated by Thorne, Miller, and Norwegian. And these are smooth manifolds with some extra structure. Then you could look at manifolds with certain cone-type singularities, like Dennis introduced, and I think his definition was that locally these would look like the following join, the join of a sphere and a sequence of manifolds. So, simple examples of that would be, say, if you take two spheres and intersect them with each other, and if you now remove, the singularity structure is just the cone on 4 points across a circle, and if you remove it, you're left with 4 disks. And another example would be this surface here, and if you collapse all the boundary components, you get another example of a C4 singularity space. The question is how to do the bordism theories of these, and how could you use them to produce actually a cohomology or homology theory. That's one thing that I started out with and tried to formalize, and if we just look at the idea, is that if you draw this very simple picture here, where you have cone-type singularities coming out, the philosophy that I adapted was to remove the singularities, so you take these away, and you get some remaining boundary components that are products of these manifolds here, and you wrap them up and make them part of the boundary structure. Then you can do sort of bordism theory in the old way. But the question is that if you have many singularities, you have many sort of complexity levels here. And the definition, this is the definition of the manifold of singularities type P1 to Pn. It's actually a system of manifolds that are being put together in a very intricate combinatorial way, which I won't really go into any details. I think I'll just say that you can do a perfectly good cobordism theory out of this. And take, for example, this simple trivalent graph here, which is a C3 manifold. It actually bounds because you can bounce via this other 3 manifold here. So this is a kind of intuition behind it, but with several singularities at a time, the combinatorics become quite complicated. Now, the idea is that singularities, they kill generators in the bordism ring. So that if you take a singularity set representing our manifolds P1 up to Pn, call that the singularity set, you can define a spectrum, consider the generalized space, such that the homotopy groups of this spectrum is the old homotopy groups divided out by the ID generated by these singularity manifolds. from this construction, lots of interesting co-homology theories follows. I've listed them up here because they have played a central role in modern homotopy theory. These are what are called truncated Brown-Peterson spectra. These do not really have names. This is sort of connective type K-theory. But these are the so-called Morava K-theories. And you see, they're just like K-theories, but they are periodic. And in some sense, they contain very essential information about or pick up essential information about the stable homotopy theory of spheres. And as a matter of fact, the first way to construct these were by using manifolds or cobordism theories with singularities. Because I remember this was in 1970, Jack Morava came to visit me and he said he had an idea that such theories would be important. And I'd been working with Frank Adams the previous year and we knew that these periodic theories existed, but no one else, I think, saw the importance of them than Jack Morava. So he said, okay, if you can construct them, I just want the existence. And the amazing thing is that just by knowing the existence of these theories, lots of theorems have been proved. And it's not until lately that one really would have to dig into the more geometric theory. But there are also now alternatives of how to construct these. And that is what I should call the May technology of S-algebras that Peter May has developed. So, in a way, we started with Bordism theories of singularities, move on to Morava K-theories, and again, they play a central role in detecting the existence or non-existence of these decaying spaces. Peter May, I think, will claim that these constructions can be done now much nicer and more efficiently by using his methods. To some extent, that's correct, but also he can't do it in all the cases. I mean, in the MU case, he can do most of it, but there are cases where I think his technology may also need to jump. So I think it's not a question of one way or the other, but maybe both. So what about elliptic homology? This is sort of a tower of homology theories. Up here we have various types of cobordism theories. Down here we have ordinary homology. You have K-theory, or I should really say connected version of it. And the question is, do we have something in between here, something above K-theory, which should also be a periodic theory? And that's sort of the candidate where elliptic homology fits into this tower. And what is it? Let me briefly say the following, that if you start with unitary cobordism, you can easily make sort of a homology theory with this, with a spectrum having this as a coefficient group. This is ordinary K theory. You could also kill off everything except x2 and x4, make x4 periodic, which is sort of a complex elliptic theory, which is close to one recently studied by Totaro in Cambridge. But the usual construction is you start with SO or spin cobordism, make two invertible, and you kill off everything except these two generators here, represented by CP2 and HP2. And you're left with a spectrum giving you a homology theory with these coefficients here. This is sort of the geometric version of constructing elliptic homology. Why is it called elliptic? Well, that's because these theories have close connections with the elliptic genus. That you really start, you have an elliptic genus taking values in such a ring or a similar ring, and you ask whether there exists a theory having these as a coefficient group. And it has, and the genus and also the form of group laws have then close connections with elliptic integrals. That's why you have the name. And there's also another way to do this by using the Landweber's exact functor theorem, which for some purposes may be, in the liquid case, a more natural way to do. But my purpose was to connect these things up in a certain way. So then I'll proceed with the next topic, namely topological quantum field theories. Let's roughly think of a topological quantum field theory as a functor from the Bordism category in the vector space, satisfying certain axioms, what I call the T and Siegel axioms. And this depends heavily on a notion of Bordism. We consider the Bordisms as morphisms. Now, could you define these theories on a more general category, more general spaces? Well, as a matter of fact, we do have a notion of Bordisms of manifolds with singularities. So we could extend it. And this has been done to some extent by Lawrence and Fried. There is a result that if you consider what they call an extended field theory, namely you take into account a codimension K manifold, you have to define a field theory as a functor from the category of, this should be the category of relative cobordisms into R vector spaces, which is the category of higher order vector spaces. Let me motivate this a little bit. The picture is as follows, that if you have a manifold M, you may assign an invariant to it, which you may actually look at as a map from the integer, from the complex numbers, and it's obtained as a pairing of cutting this manifold up in two pieces, M1 and M2, along a manifold here, sigma. And it follows that each of these are vectors, and they are members of the vector space Z of sigma. Now you can go on and decompose sigma in two parts again, and ask for a pairing of Z of sigma, which is now a vector space. So what objects would have the property that they would pair into giving you a vector space? Well, the answer to that is a notion of two vector spaces. And what's that? A two-vector space is a special case of a higher category. So a higher category, this goes back to the Aristotle Wotendy, is that you consider objects, one morphisms, two morphisms, and higher morphisms. So in a sense here, if you compose morphisms here, you deform morphisms through two morphisms. So a two category, you have morphisms between morphisms. And these can be composed in two ways, horizontally and vertically. And gives a very kind of delicate combinatorics. But for higher ends, I think a good definition is still underway. Now, a two-vector space is in a sense a linear space over the category of complex vector spaces. If you think about what that means, you end up with the following definition, which is due to Kapanov and Lubotsky. So I'll find the two category of two vector spaces. The objects are numbers n and m. The one morphisms are matrices of vector spaces. And the two morphisms are linear transformations between the vector spaces in matrices. And composition is defined as follows. You may think of this as rank, and represent this actually as category, namely vect n. So that a two-vector would be then represented by a sequence of vector spaces and acted upon these matrices as follows. So this is the composition. Well, back to Bordism theories with singularities. The idea was sort of to remove the singularities, and we got a very delicate sort of hierarchical structure on the boundary. So we have a sequence of submanifolds, and then thinking about a relative version of topological quantum field theory and extending these axioms, it's clear then that extending the philosophy of Lawrence and 3, that we will get an extension from the Bordism category of manifolds and singularities, but not anymore into vector spaces, but into Vn, namely higher order vector spaces. And n would depend on the singularity structure. So from this we can construct various sort of functors. We could think of, if we have a functor from a topological spaces into categories, and think of representations then of this category in Vn. And we could define an object as follows: kc of nx equal to the set of all functors from C of x into Vn. Think of these as kind of bundles and take a kind of Brook construction. I'm being a bit very general at the moment, but I'll end up being quite explicit at the end. If we take C of x to be the Bordism category above the topological space x, we could form this functor Knx, which consists of all functors in a reasonable sense preserving the relevant structure from Vn of x into Vn. What does this look like geometrically? Well, if m equals 1, m equals 0 and n equals 1, we basically have the path category, and we are looking at functors from P of x into vector spaces. And basically that gives us kc, as pointed out by Ramsey. Pardon me?
Is a bottom category the category also? What is category?
Some people claim that, but I wouldn't claim that it is an n category since we don't.
If we have a category, what's part of the category automatically?
Well, you could put on, I mean, in the case, say with P of x, you could put on a trivial top structure. But I mean, I'll organize P of x, yeah.
Also, that's on the bottom.
Yeah, yes. But I mean, there are various ways to do that. But, yeah, okay. Wait a minute. This basically gives us ordinary kc. If you look at the Bordism V1 of x into V, that's basically mapping objects like this into x, namely surfaces where the boundaries are families of circles. And this is what Ramsey in his Bourbaki talk in 89 said that should be related to elliptic homology. I asked him quite recently about this, and he said, I'll think about it. And 3 days later, he came back and told me, I looked at my notes and I had no further comments. So, but the general idea is that if we have a topological space, we could sort of erase n vector spaces and look at a kind of generalized K-theory. And that's what I'm suggesting, that we look at the case of n equal 2. So this K02 is a version of elliptic homology. Well, let me just briefly say what chromatic filtration means. Generalized homology theories could be filtered in a certain way, namely depending on how much of the homotopy theory of finite complexes they detect. So rational homology of homology is filtration 0, topological K-theory filtration 1, Urala K-theory is filtration n, and complex cobordism in this sense has filtration infinity. Elliptic homology is supposed, or often one define a theory to be an elliptic homology theory if it has filtration 2. Pardon me? Not, they're related, but not the same, because, yeah, they are. So I'll define a second order K-theory. This is some recent work with my colleagues Dundas and Romnes. So let's look at what should an algebraic 2K theory be. Let's start out with a symmetric bimonoidal category, strict associative, And this is a two category where the objects are, as I just described. The problem now is that we want to define sort of a general linear group for matrices. And this is, if you look at objects here, and in a fully quadratized form, Vij will consist of matrices of positive integers. And of course, there are not many isomorphisms for those, only permutations. So if you look at matrices now with one object different from zero, only one, at most one object different from zero, embed that in all kinds of matrices in this category B, which we now look at as a kind of ring type structure. The idea is that this is a stable equivalence. So the idea is that in order to have room enough and get enough isomorphisms, you move into the homology category and stabilize these. Then you can get enough isomorphisms. This is a rather technical construction coming from algebraic K-theory, that you stabilize the category V by forming a certain limit. This is what is called an FSP, a functor with smash product. It's a technical name. And you also have to stabilize the matrices. So you stabilize the category and the matrices. Then we can form an algebraic K-theory over these. But we have to be careful how we stabilize the matrices. First, we should form these simple matrices and then stabilize afterwards. It gives a different result if you stabilize in a different order. So let me come to the result. Okay. What we do is that we have this stabilization here. We have a map phi naught into the matrices of K naught of B, which actually is a ring. So we can form a pullback here and form this object here. That's our candidate. This is a group-like object, so we can use a bar construction and form this direct sum here. And then the definition now of the algebraic 2K theory of the category C is that we take this object coming here, we use group completion, and that's the space representing it. So, of course, you know, if you take a ring and just look at GLN of A, this is the space representing algebraic K theory of the ring. But now, you can use this theory of FSPs, and what you end up with is the following, that 2K of B mod is modules, free modules over the bimonoidal category B, is algebraic K theory of KB mod. So if you put B equal to vector spaces, then it's known that this KB is connected to K theory. And this ends up with a very simple calculation. It's not very simple, but the result is simple. Yes? Yes, I'll finish very quickly. That 2K vect mod is algebraic K theory of connected K theory. And this has just been calculated by Romness and Stony, and it's shown that it has filtration too. So it's an elliptic homology. So it shows that this theory, based on two vector spaces, is represented by this spectrum here in the S-algebra sense, and it has chromatic filtration too, and hence is a concrete model of elliptic homology. What happens for, and this can be related then to two vector bundles, as we do for K theory, but what happens for higher ends and three vector spaces has not yet been worked out. But at least, I think this is the first concrete model of any elliptic homology. Okay, thank you.
Okay, any questions?
connection would be through conformal field theories, as Siegel suggested. But no one, I mean, you really like sort of space of all field theories, make that into a kind of infinite loop space, and that should represent the homology theory. But no one has been able to confirm that. So the connection is indirect, like this, but two vector spaces seem to play a role in for example, Siegel's work on conformal field theories. I mean, that's where it came from. In Siegel's theory of conformal field theory. Yeah. I mean, the work that he and Ulrike Tillman did is sort of using two vector spaces.